Alrighty, good morning honors chemistry students. Today we're going to be taking a couple notes on energy and how energy looks specifically related to electrons. So you should be on page 1 of your notes. We're looking at Bohr's electron emissions in quantum mechanical models. So the notes look like this. You should have this out in front of you and be ready to take a couple notes. So, properties of light and the wave description of light. So, electromagnetic radiation. We talked about radiation in our last unit, but electromagnetic radiation is specifically a form of energy that exhibits wave-like behavior as it travels through space. So, we talked about radiation and how radiation is how things travel in waves. We talked about convection, how things travel in currents, and also conduction, how things travel through contact. But radiation is specifically how energy travels in waves, and we're going to be focusing on waves throughout this whole unit. As always, if you need more time to write things down, make sure you just pause the video. So the electromagnetic spectrum, you've all heard of this whether you know it or not, but it's basically all the forms of electromagnetic radiation. And it looks like this. Okay, you've all seen this. You all know what this is. You all have visible light. You know what gamma rays. You've heard of X-rays and UV rays and infrared waves and microwaves and radio waves. This is our electromagnetic spectrum. And here in the middle is the waves that we can see. Okay, our eyes are able to detect those waves and we see them as color. So we're going to be talking about how these colors happen, why we can see them, and things like that throughout this whole unit so that we can connect back to our original phenomenon of why different elements emit different colors. So some other terms for you is wavelength, and wavelength is denoted by this little symbol, this upside down Y, that's called lambda. Okay, and wavelength, the definition is just the distance between corresponding points on adjacent waves. Okay, so I can show you what that means here on this other picture. As you can see, a wavelength is this is our whole wave, this whole thing. Our wavelength is the distance from the tip of one wave to the tip of the next, or the crest or the trough of one wave to the next one. You've probably heard about like a crest and the trough of the wave maybe in middle school. So the wavelength is how far apart the waves are. Okay. Whereas frequency is denoted by this letter V, is the number of waves that pass a given point in a specific time. So usually 1 second. So how fast is it going up and down? Okay, the wavelength is how frequent things are happening. And wavelength and frequency are related to one another. Okay, they're related to one another through this formula where C equals wavelength times frequency. Okay, so we're multiplying them together to find the C, but we don't know what C is yet. C is what we call the speed of light, and you will need to know this value. So the speed of light is measured at 2.998 times 10 to the 8 meters per second. That is how fast light travels. Okay, how fast light is traveling is due to its frequency times its wavelength. Okay, and we're going to be calculating some different things using that formula. Okay, so we know that lambda is wavelength, and it's always measured in meters. What you do need to know is that 1 meter is equal to 1 times 10 to the 9th nanometers. Okay, and like I said, V is frequency, and V is always measured in seconds to the -1, or what we call hertz. Okay, Hz, hertz. So we're going to do a quick practice problem together. So we're going to be calculating the wavelength of the electromagnetic radiation in nanometers, whose frequency is 7.5 times 10 to the 14th hertz. So just like we've always done with our practice problems, we're always going to write down what we were given first. So let me pause my video real quick and write this on our board for us. Alrighty, so I just wrote down what we were given. We're looking for wavelength, so it's unknown. We were given that frequency is 7.5 times 10 to the 14th hertz, and that we know that the speed of light C equals 2.998 times 10 to the 8th. Remember, the formula we're using is speed of light equals wavelength times frequency. So all we're going to do is plug our values in. Okay? Let me check and see this. So we're going to have 2.998 times 10 to the 8th meters per second equals our wavelength times 7.5 times 10 to the 14th hertz. Okay, remember that hertz is the same as seconds over -1. Okay, so hertz equals the inverse of seconds. So what we're going to do is divide by both of these on both sides. I'm going to use S-1. We can now see that we have S on the top and an S-1 on the bottom, so we can get rid of those technically. And we're going to divide these, okay? And when we divide these, we get an answer of 3.997 times 10 to the negative 7 meters. Okay? If we were looking for our answer in meters, we would be done here, but remember it wants our answer in nanometers. And I told you that in 1 meter, there's 1.0 times 10 to the 9th nanometers. So remember, we got to bring back dimensional analysis. We have meters on the bottom, or on the top, we need meters on the bottom. So 1 meter is going to be equal to 1 times 10 to the 9th nanometers. We can cancel out our meters on top and bottom to get our final answer of 399.7 nanometers. And if we use sig figs, look at, we started with 1, 2, and 1, 2, 3, 4. So we can use 2 sig figs, so we can round that to like 4.0 times 10 to the 2 nanometers as our final answer, or 400 nanometers. Okay. Your homework today is going to be to look at some more practice problems like that. I think it is time for homework now, so let me make sure I don't have any other notes to go over. Maybe I have some more. I have some more, I lied. Let's keep going. Actually, I lied again. I'm going to pause temporarily, and then we're going to continue on into our next video. So make sure you know how to do this well. Let me know if you have any questions. Thank you.